physics for ham radio. It was a graduate level physics class, and I've shared with the club a couple of times now about my experience with that class, and it was delightful. The professor is actually the chair of the astrophysics department at Rice. Her name is Pat Rife, R-E-I-F-F, and her call is W5TAR, and she just loves ham radio. But a fascinating lady. She's done most of her academic work has been on studying plasma, which of course is relevant to the work that we do with the ionosphere. But she also started her career working on the Apollo 14 mission. So really a fascinating person, and it was a real joy to learn from her this past semester. So we had to do a final project, which is a presentation on a topic of our choosing. And I decided to sort of delve deeper into WSPR. So that's what I'll be presenting on this evening. So just as a show of hands, how many of you have used WSPR or played with WSPR in some respect? If you have, maybe just put that into the chat as a yes or a no, just to give me an idea. Okay, great. Yeah, very good. So WSPR is an interesting mode, and a lot of the algorithms behind it have made other modes that we enjoy, like FT8, possible. So I want to delve into some of the computer science behind WSPR, as well as some of the benefits to the radio hobby. Okay. So this is what we'll talk about in the Elmer session. So what is WSPR? How does WSPR aid in studying ionospheric propagation? How does WSPR achieve communication with low power and in poor conditions, much like the other WSJT modes? Which error correction method does WSPR use, and how can WSPR aid in citizen science initiatives? In particular, what can we do as radio amateurs to help contribute to the science of understanding better the ionosphere itself and how radio propagation on the HF bands works? So most of you probably are aware of the creator of the WSJT modes, including WSPR, Joe Taylor, who's a Princeton physicist who won the Nobel Prize in 2008 for his work on quasars. If you ever have a chance to listen to some lectures by Joe Taylor, I really recommend it. He's a very interesting guy, very down to earth for all of his scientific accomplishments. And the story of how the WSJTX suite came about is really interesting. Joe Taylor will say, he's traditional astrophysicist. He's not a software engineer. He's not a computer scientist, but he did what he had to do to make these weak signal modes possible. And of course, some of his early interests were in things like moon bounce and meteor scatter. And, the key to these modes working is the underlying digital error correction for the messages. And so Joe Taylor very humbly says, I'm not a computer scientist, but I learned a lot about communications theory and obviously programming to help bring the software that we now all enjoy to fruition. So I am going to talk a little bit about some of the underlying computer science behind WSJTX. And I'm not a physicist, but I do have a background in computer science. I teach computer science, so that's an area that's of particular interest to me. So as we know, the WSJTX suite is designed for studying radio propagation, in particular with low power and in less than ideal conditions. And as we're coming out of the low point of the previous sun cycle and sunspot cycle and coming into cycle 25, FT8 and those modes really did help us make contacts under poor conditions. And WSPR itself is not a bidirectional contact mode. It's more almost like a beacon. And tonight we're going to talk about why it's important for us to participate in WSPRnet as much as we can to contribute data to the study of the ionosphere. So a WSPR signal is a digital signal, and the transmission includes 50 bits of information. 28 bits is our call sign, 15 bits is our grid locator, and then we self-send a power report. So we say how much power we're transmitting with, and there's 7 bits allocated to that for a total of 50 bits. Now, we end up sending a good deal more of information, more bits than 50, that is, because of the error correction built into the protocol. So the WSPR signal ends up looking something like what you see there below once it's finally encoded. And you can see there's quite a few more bits there than 50. These tools, in particular WSPRnet, are really powerful for sensing the behavior of the ionosphere in various phases of solar activity. And the WSPRnet itself is a database, a centralized database on the internet that includes voluntary participation from hams like you and me all over the world who are providing real-time data in terms of propagation conditions. And it has immense potential for collecting these kind of data, which scientists can use to understand it better. In fact, Nate Frizzell, who's talked to, Dr. Nate Frizzell has talked to our group on several occasions, and I think is going to speak at Tim's Propagation Summit in January, said that MF and HF propagation data WSPR has produced MF and HF propagation data with greater spatial, temporal, and spectral coverage than any prior amateur radio citizen science experiment. And really what we're getting is big data in the cloud that are just massive amounts of reports from all over the world. And many of these are running continually, sending what signals you're hearing, how far away they are, how much power was being used, what time of day is it, what are the space weather conditions at that time. And when you have that many data points, you can begin to conduct really powerful research. So you, for example, correlate what's the difference, or what's the relationship between current solar activity and the number of stations that were heard on the WSPR network, for example, or the distance between stations that were heard, or the furthest distance or the shortest distance, particular continents, the northern and southern hemisphere. I mean, the possibilities are just endless in terms of the kind of research that can be done once those data are collected. And of course, that's all post hoc research. The data's all collected, and then you run different models on the data. So as you know, these modes are very low, or intended to be low power, with a very high signal to noise ratio. And so when conditions are poor, the signals get through, and that's made possible because of these error correction algorithms behind WSPR. So here's some examples. Of course, I think most of you have used PSK Reporter. And WSPRnet has a very similar map that shows which stations have heard a particular transmission. And then all those data are archived in a giant database for future use. So the power behind this, how it actually works, is because of the error correction algorithms that are built into the protocol. And any digital message, whether you're transmitting through a serial port or as we do, through electromagnetic waves, there has to be some level of error correction to ensure that what was transmitted and what was received are the same thing. And there has to be some level of controlled redundancy so that transmission errors can be recognized on the receiving end and corrected. And the simplest way this is done is by simply repeating each symbol in a message. And that's the simplest and most trivial form of redundancy. So you just send the same message several times and you compare it and see if any particular messages have missing bits or incorrect bits compared to all the others. But the method that's used by WSJTX and WSPR in particular is called forward error correction, which is a very particular type of algorithm. So what's generated is called a code word. And this is a redundancy of bits from those 50 bits in the WSPR message that can be arranged by mapping each sequence of K number of message symbols in a controlled way to a unique and longer sequence of N number of symbols called a code word. And the mathematics behind this in this K to N mapping, and then on the receiving side, the N to K reverse transformation, is a major branch in modern communications theory. And I will not even presume to understand in detail precisely how these algorithms work, but I'll give you kind of a bird's eye view from my own understanding. So what's transmitted what's necessary in order to decode the message is a ratio called the code rate. So that is for every N symbols or every K symbols that are sent, how many N symbols of redundancy are there and vice versa. And that gives us a ratio to know, okay, we're expecting X number of bits, but really the message that was transmitted is only Y number of bits, or in this case, K and N. So we can easily see that N minus K gives us a number of bits that are redundant in a particular transmission. And WSPR uses a certain constraint length and a particular ratio of a 1 to 2, which is pretty simple. Now for the algorithm that's used, called a convolutional code algorithm, 32 is actually a relatively high number, which ensures that those bits get sort of ramrodded through each 2-minute transmission of WSPR. So I won't go into this in much detail. Suffice to say that the algorithm that's used in computer science terms is a finite state machine, and in algorithmic terms. And these kinds of convolutional code algorithms are used in all other applications, like our streaming digital video, cellular data transmission, satellite transmission, so on and so forth. In convolutional code algorithms, they can be recursive or non-recursive, and WSPR happens to be a non-recursive algorithm. So in this process, each sequential bit depends not only on the current input into the algorithm, but the previous inputs. So there's a pattern that emerges based on previous inputs of bit by bit into this algorithm, and then the redundant bits that are produced. So it basically takes the 50 bits that are used in the intended message. That's our call sign, our grid locator, and our power level, and extends that to 162 one-bit symbols. So it takes a 50-bit input and produces a 162-bit output that's actually transmitted. And so all of those excessive bits are for the purposes of error correction. So if you think about this, this is what's really remarkable is you look at the combinations and permutations of what's possible in that 50-bit message. If we take the 28 bits for a call sign and 15 bits for a grid locator, if we consider a 1 or 2 character prefix for every standard amateur call sign, followed by a number, followed by 1 to 3 characters in the suffix. With those simple rules, we're looking at a possibility of 262 million possible call signs that the software has to account for on the receiving end. I mean, it's pretty mind-boggling, you know. And the same thing is true for grid locators. So we can do the math there, and we end up with approximately 32,400 possible grid locators that are encoded with just 15 bits. And so, you know, what the software has to account for on the other end in terms of checking the validity of the possibilities is really astronomical. I think if you've used any of these modes, you know that your computer's clock has to be accurate within 1 second of UTC time. And there are ways to sync the computer's clock either with external software. Sometimes if you're using Windows, the Windows time servers are not, the Microsoft's time servers aren't always great. So there's third-party software that can be used. But syncing with the time is really important because the software is expecting the 162-bit message every 2 minutes on the money in UTC time. And if your timing is off, you're going to miss bits in the transmission, and it's not going to be decoded properly, or if you're transmitting, it's not going to be encoded properly either. So there are basically a series of 9 steps from transmission to receive in WSPR. And again, be thinking, these apply to all of the digital modes. We're just happen to be talking about WSPR tonight. Well, the WSJTX modes, I should say. So the first 5 steps are on the transmitting side. So the software is going to generate a message. So that's, my call, maybe, CQ, my grid load, well, not with WSPR, but if you're using FT8, for example, you might do a CQ. WSPR, I'm just transmitting a fixed message of my call sign, a grid locator, and the power. So the software generates the message. It compresses those 50 bits into the 162 bits with all the error correction from the forward error correction convolutional code algorithm. So then it produces this code word of n number of symbols. And then it adds a synchronizing pattern and modulates that onto a carrier and then transmits the waveform over the radio channel. And most of these digital modes use phase modulation for the transmission. And then on the receiving side, you're going to receive that message every 2 minutes on the money. In WSPR's case, FT8 is 15 seconds. Receive it, synchronize and demodulate that signal to yield n symbols, which we know we were expecting to decode 50 bits out of the 162 that were sent. And we know that some of them might be in error. So you work through all that redundancy to see if you can recover K error-free message symbols. So K being 50. We're expecting 50 error-free symbols on the other end. The data are decompressed, and then the message is presented to us in human readable form. So translated from binary into ASCII, and we able to read it on the screen. And then we receive that message. And of course, the most important steps in this whole process, according to Joe Taylor himself, are steps 3. That's the error correcting redundancy to produce the code word. And step 7, decode and received symbols to recover K error-free symbols. So all the power is really in the error correction that's happening in these weak signal protocols. So what's this have to do with us? Well, Dr. Frizzell has talked about the importance of hams participating in citizen science initiatives. And he founded the HamSci initiative to get us involved in contributing data to these big data repositories so that the scientists can do the work that needs to be done to understand the ionosphere better. And so, for example, this professor at Rice that I just studied under, she's a plasma scientist. And so she's studying ions, ionized gases in the ionosphere and on the sun's surface. And this kind of data from all over the world, from hams all over the world, will help her to identify patterns and relationships between all kinds of different independent variables that she can parse out. So we can all participate in this kind of citizen science initiative. We don't even have to tie up our own transceiver to do this. I mean, it does seem like kind of a waste to have a nice rig sitting on WSPR all day long, just decoding symbols. Well, we don't have to. We can use very inexpensive hardware and set up and what I'm going to show you is a Raspberry Pi scenario, where we can, either just let it sit all day and receive symbols and decode and report propagation back to the WSPRnet database, or we can even transmit. And I'm going to show an example of how we can do that without tying up our primary rigs. So this is a project I've been working on for a while, and this is actually modulating a signal off of a Raspberry Pi GPIO pin. So we can actually take one of the pins on Raspberry Pi's GPIO header and modulate a digital signal. You end up with a very ugly square wave, but it's still modulating voltage off of that pin. And we can actually transmit. Now we're transmitting at about 10 milliwatts. But we are transmitting with no additional hardware. So this is just a plain old Raspberry Pi, no radio involved. So we don't need an extra transceiver or transmitter. We're transmitting just off of the bare metal, the hardware on the Raspberry Pi itself. Now the key is we need to have a low pass filter to smooth off that square wave that it produces. Otherwise you get harmonic splatter all over the place. So this is just a simple schematic of a low pass filter, and you've got 3 inductors and 4 capacitors, and you just run that square wave through this circuit, and you get a relatively clean signal on the other end. And I've been tinkering with this for a couple of weeks now, playing with different filters and trying to come up with some things that worked. I was just soldering a 20-meter low pass filter before this call, and I'm almost done. I wanted to have it done before we did this so we could try it out. But I have a 10-meter one built, so maybe we'll experiment on 10 meters a little bit with transmitting from the Raspberry Pi. This was one of my first attempts at building the filter, and I had some stock inductors there. These are 0.33 microfarads. And this design didn't really work out too well for a couple of reasons. The first one that I discovered that's a real pain, and I'm working on a solution to make it as clean as possible, but these leads that you see coming from the GPIO header on the Raspberry Pi to the filter board are too long, and those are only about maybe 3.5 inches long, and they're just too long, and they're antennas. And so they're just, releasing voltage out everywhere, and they're working like a transducer. And so I learned quickly that I have to shorten my leads, directly to the pin as much as possible in order to get this to work effectively, and to reduce as many of those spurious emissions as I possibly can. So this is my second design. This is a 10-meter filter again. And these leads are still too long. I've actually clipped them down and put a screw terminal here at the end. And I'm working on some female pin headers that will just snap right onto the GPIO pins themselves, which is about as short as you can get. But as you can see, I wound my own inductors here, which got me much more precise values. And so there's my 3 toroids and my 4 capacitors for my 10-meter filter, and the signal's cleaned up quite a bit. So with that, you can actually do some WSPR transmitting without tying up your rig and using just a stock Raspberry Pi. For receiving, you can get one of these SDR dongles for about $25 on Amazon, and just let it sit and receive WSPR signals all day long and report those signals back to the WSPRnet database. And that's how we can contribute to collecting data for the scientists to begin working with. So this is a very inexpensive setup that you can do without tying up your primary rig. So here's Dr. Frizzell at a field day event, and here's an example. I think he actually talked to our club about this a few months ago. But one of the primary examples was collecting valuable data during the 2017 solar eclipse. So now he had hams all over the world collecting data about what effects a solar eclipse have on propagation. And all of us contributing those data help them then to study it after the event is over and to look for discernible patterns. So that was one of the most recent examples of how we can contribute to the actual science. So with all that said, here's kind of the summary and conclusion. WSPR and the WSJTX suite have opened new doors for radio amateurs to operate with low power and in weak conditions. I think we've all enjoyed the fruit of that. But here's what I think is most interesting, and I think really cool about this whole suite of software. I know there are plenty of hams that say that FT8 is ruining ham radio, but what I find fascinating is the interdisciplinary nature of projects like this. I mean, this has involved, of course, radio physics, but also computer science and communications theory, all working together to make something possible. And even if you have disdain for FT8 and the laziness involved in making FT8 contacts, you got to appreciate the interdisciplinary science behind this suite of software and what it's made possible for us. And then, again, WSPRnet allows us to contribute, to actually be data collectors for the scientists. And we can do it with very low cost, very low commitment. And, without tying up our primary rigs, we can have something sitting and collecting data, to be a part of something bigger than ourselves. So that concludes my presentation for the Elmer session this evening. I thought maybe something fun would be to actually see if you guys can hear me on 10 meters. So before we do that, any questions or comments or thoughts about what I shared this evening?
Josh, I have a question on the output of the Raspberry Pi. Mm-hmm. So going into your filter board, I know you've designed the filter board for 50 ohms in, 50 ohms out. At least I'm guessing. Yes, theoretically. So do you know what the output impedance is of the Raspberry Pi?
I don't, because it's really DC. So if you think about it, I mean, it's not putting out an AC current. It's modulating a DC voltage. So you've got a ground pin, DC ground, and a DC, modulation that's just a square wave. So I'm not sure how to measure that, Tim. I don't know. I mean, so really, I mean, we're cheating. We're taking a DC square wave and converting it into, faking a sine wave on the other end of the filter board. That's basically
right. Right. And remind me again what the power output of that?
10 milliwatts.
10 milliwatts.
Yeah.
And I mean, because the filter performance is going to be, somewhat dependent on getting all the impedances set right.
Right. Mm-hmm.
And what frequency on 10 meters? So is this?
Hang on, I will tell you. It's the set WSPR frequency. So let me see here. And if maybe while I'm gonna get set up, but I don't know if anyone else has any questions or comments or thoughts on what I shared this evening.
Hey Josh, it's Bob. It was a great presentation. I always wondered how this worked, so I never had the time to look into it. So I really appreciate you explaining it. It was really good.
Thanks. Yeah, I really enjoyed learning about it, and just a lot of Joe Taylor's articles are publicly available, and some of them he published in QST, so they're out there for our consumption.
Yeah, information. So I appreciate it. Thank you.
So yeah. Bruce had a question in chat there, and Bruce was asking, geez, where did it go? Is there a web page that describes your Raspberry Pi hardware setup?
Yeah, I just sent the GitHub link for the software. It's called Raspberry Pi, which it just runs from the command line in Linux in the Raspbian operating system. And there's step-by-step instructions on how to do it. And Bruce, you just connect up to its GPIO pins 7 and 9, I think. And one's DC ground and one is, the modulating pin. And then you would hook it up to this filter board. And there's a link on the page that I just posted that actually gives a really nice little article on how to build these harmonic suppression filters. And it gives precise values for all the inductors and capacitors. But then he very conveniently gives us off-the-shelf options for each band, which is really handy. Now, again, I recommend winding your own inductors. It's not that hard. And these are T37-6 toroids, which are pretty easy to find as well. And you can get the number of turns right off of that